Imagine a world where the most complex problems, things that would take today's fastest supercomputers millions of years, are solved in seconds. Imagine curing diseases before we even notice symptoms, or eliminating traffic jams instantly. It sounds like science fiction, but quantum computing is making this possible. So, what exactly is quantum computing? How does it work? And why is everyone so excited about it? Let's break it down simply. Before we dive into quantum computers, let's talk about classical computers, the ones we use every day. They work using bits, the smallest piece of information, which can either be 0 or 1, like a light switch, on or off. This system has worked for years, but as problems grew more complex, classical computers began hitting their limits. In the 1980s, physicist Richard Feynman realized that classical computers couldn't simulate the behavior of atoms and molecules. Why? Because at that tiny scale, the rules are different. Feynman suggested we needed computers that operated on quantum principles. That's when the idea of quantum computing began. So, what makes quantum computers so powerful? At the heart are qubits, which are like classical bits, but way more interesting. A qubit isn't just 0 or 1. It can be both at the same time. This is called superposition, and it's one of the key reasons quantum computers are so powerful. Imagine flipping a coin. When it's in the air, it's neither heads nor tails, it's both. Qubits work the same way, allowing quantum computers to process far more information than classical ones. But there's more. Quantum computers also use a principle called entanglement. When qubits are entangled, changing one qubit affects the other instantly, even if they're far apart. It's like rolling two dice. Roll one, and the other one rolls itself, no matter how far away it is. Together, superposition and entanglement allow quantum computers to perform calculations that classical computers can't even imagine. They can solve problems in seconds that would take supercomputers thousands of years. What does this mean for us? Let's explore some real-world applications. One area is cybersecurity. Quantum computers could crack encryption methods in seconds. With Shor's algorithm, they could break codes that are virtually unbreakable today. This means we'll need new encryption methods, quantum-safe encryption, to protect our data. In medicine, quantum computers could revolutionize drug design. Today, simulating molecules and testing drugs is slow and computationally expensive. Quantum computers could handle these simulations in no time, helping us discover cures for diseases like cancer and Alzheimer's much faster. Quantum computing could also accelerate AI development. AI systems process huge amounts of data to learn patterns, but the more data there is, the longer it takes. Quantum computers could process data in parallel, making AI faster and smarter. This could lead to better self-driving cars, personalized medicine, and more advanced tech. In logistics, quantum computers could optimize delivery routes, solve supply chain problems, and improve city traffic management. Companies like UPS and DHL currently rely on classical computers, but quantum systems could save time and resources, revolutionizing industries. So, what's the big picture? Quantum computing isn't just about faster computers. It's about reshaping industries and changing how we live. As quantum computers take over certain tasks, we could see shifts in jobs. Some roles may disappear, especially in traditional cybersecurity, but new opportunities will emerge in tech and research. Countries that lead in quantum computing will have a competitive edge. The US, China, and the EU are investing heavily in this technology, and whoever gets there first could dominate the global economy. Let's not forget the ethical questions. If quantum computers can break encryption, what happens to our privacy? These are important concerns we'll need to address. The potential of quantum computing is huge, but we're still in the early stages. There are challenges, like building stable qubits and scaling systems, but progress is being made. For instance, Google's Sycamore processor completed a calculation in 200 seconds that would have taken the world's fastest supercomputer 10,000 years. This marked a milestone in quantum supremacy. Quantum computing won't replace classical computers anytime soon, but it will complement them, solving problems once thought impossible. The future of quantum computing is closer than we think. Whether it's curing diseases, improving AI, or securing data, its impact will be profound. But as we develop these systems, we must use the technology responsibly. The real question is, are we ready for the quantum future?